we have the pleasure of hosting Marcus Pivato. Marcus is a professor of economics at Cergy Université, and he is, I would say, he is some example of embodied interdisciplinarity. He has Marcus has had a previous academic life working in mathematics and dynamic systems. His current research are in the area of economics, social choice theory, well, basically theoretical economics, but also reaching out towards philosophy, political philosophy. Marcus came to Cergy 7 years ago with the holder of the Chair of Excellence funded by the Center of Excellence called LABEC, maybe, to the Center of Excellence in Mathematical Modeling and Economics. And today, Marcus will tell us what normative economics is about. So, Marcus, you have the floor until 2 o'clock, questions included. So we let you manage time and questions as you wish. But it's pretty statement and for questions and discussion. Thanks a lot, Marcus.
For accepting to give the first reaction to hear.
Thank you very
Very
much. So we're just going to wait a couple of minutes because share the screen for the people who are joining us on Zoom. Great. Okay, so let's get started. So I'm going to be talking about economics, and when you normally think about economics, you probably think about markets and prices and production and consumption and taxes and Brexit and things like that. But that's not what I'm going to be talking about. I'm going to be talking about a different kind of economics because, in fact, economics has 2 aspects to it. This is not working. Now we don't have a clicker. Like this. Well, start quicker. Right, so economics has 2 aspects. The first aspect of economics is what we call descriptive economics. So that is the part of economics which deals with questions about how societies, individuals do make decisions. But in fact, I'm going to talk about something different once I figure out how to get this to work properly. Great. I'm going to be talking about normative economics. And so normative economics is about a different question. It's about ideally how individuals or societies should make decisions. So roughly speaking, you could say that descriptive economics is economics seen as a kind of science. Whereas normative economics is really more looking at economics from a philosophical point of view. And so normative economics has 3 branches. Roughly speaking, so the first branch is decision theory. And so decision theory basically looks at questions about how rational agents would make decisions. So the question is, how should an ideal rational agent make decisions when faced with uncertainty or indeterminate trade-offs or other kind of complicating factors? The second branch of normative economics is social welfare theory, and this is basically looking at the question of how we should evaluate social arrangements in terms of criteria like fairness or equality or aggregate well-being, how we should make trade-offs between different people, how we should do that cost-benefit analysis. And the third branch of normative economics is social choice theory, which is about the design and analysis of systems of collective decision-making, mainly voting rules. So in a nutshell, you could say that decision theory is about rationality, and social welfare theory is about justice, and social choice theory is about democracy. And so those are the things that I'm going to be talking about today. So basically, I'm going to spend about a third of the talk on each of these areas. So let's get started by talking about social choice theory. So basically, social choice theory starts with the following question. What is the best way for a group of people to make a decision, right? And of course, the obvious answer that is very popular nowadays is we say the best way for a group of people to make decisions is with democracy, right? Democracy is good. But the problem is, what exactly do we mean by democracy, right? You might think that democracy is kind of an obvious concept, but it turns out that when you examine democracy, it turns out that democracy is actually quite ambiguous and complicated and problematic. So to see an example of that, let's consider a simple example of an election. So here's an election which has three candidates. I'm going to call them Alice, Bob, and Carol. And this symbol here, this funny sort of greater than symbol, basically indicates preference. It indicates that voters think that somebody is better than somebody else, right? So, for example, the first line of the table is telling us that 40% of the voters prefer Alice over Bob, and they prefer Bob over Carol, right? So they think Alice is better than Bob, and they think Bob is better than Carol. Okay. So let's suppose that we just run an ordinary election using plurality votes. So what's going to happen? Right, what's going to happen is obviously Alice is going to win the election, right? Because 40% of the voters think Alice is the best candidate, whereas only 25% of the voters think Bob is the best candidate, and only 35% of the voters think that Carol is the best candidate. So Alice wins the election. Okay, so democracy is spoken. But there's a problem, right? And the problem is that actually 60% of the voters prefer Bob to Alice. Right? As you can see from looking at the table, right? I haven't done any magic, it's the same numbers. 60% of the voters prefer Bob to Alice. And 60% of the voters also prefer Carol to Alice. In fact, 60% of voters think Alice is the worst possible candidate. So how exactly did Alice win the election when 60% of the voters think that she's the worst possible candidate? Right? So I think you can probably guess what happened here, right? What happened is, even though 60% of the voters think Alice is the worst possible candidate, those voters were split between Bob and Carol, which is a very common problem with plurality voting. And so the obvious way to fix this problem is to hold a runoff election between Alice and the candidate who got the next highest number of votes, right? This is how we run presidential elections in France. We have a runoff vote precisely to avoid this kind of problem here. So let's do that. Let's have a runoff election between Alice and the second candidate. In this case, the second candidate is Carol, who got 34% of the vote. So if we do a runoff election with these numbers, what do we see? Well, we see that Carol wins the runoff election with 60% of the vote, which is exactly what we expected was going to happen. But there's a problem, which is if you look at the data in this table, 65% of the voters prefer Bob to Carol. Okay, so that means that even with the runoff vote, the wrong candidate won again. So this is a bit disturbing. So what this shows us, basically, this example shows us two things. First of all, plurality voting rule is a terrible way to elect presidents. Somebody should send a memo to the United States. And second of all, runoff votes do not fix the problem. Okay, so neither one of these procedures is very good. And by the way, I think that you can tell looking at the numbers in this table, these are not exotic numbers. I have not come up with some kind of exotic, super contrived example. These numbers look completely reasonable. So what should we do? Well, one diagnosis, one problem with plurality voting and also with the runoff vote is that it only looks at voters' most favorite candidate, right? It only looks at the candidate at the top of the list of preferences. It doesn't consider the rest of the data in their preferences, right? It doesn't look at who they thought was the second best candidate and the third best candidate. That information might be relevant. So why don't we take that into account? So, for example, we can have a voting rule where we give 2 points to each voter's top choice, and we give 1 point to her second choice. Okay, and then we add up all the points, and the candidate with the most points wins, right? So, for example, let's consider the data in the following table. Okay, so here we see that, like, for example, 45% of the voters think Alice is better than Bob, better than Carol, etc. All right, so let's do this rule. Okay, so for example, let's look at Bob, right? So Bob, the voters in the first row of the table rank Bob second, so he picks up 45 points from the 45% of the voters who put in a second place, right? And then he picks up 2 times 35, which is 70 points from the 35% of voters who put in the first place. And so if you add up all those numbers, you see that Bob ends up with a total of 115 points, which is more than either of the other candidates, and so Bob wins the election. Okay, so this is the way that we can take into account people's second choices as well as their first choices. Notice that the plurality voter here again is Alice, but the point is Bob wins the election effectively because he picks up points from being in second place for a lot of people. All right, so this rule is called the border rule. It was first proposed by Untitled Chapter, who was a French mathematician around the time of the Revolution. It has some nice properties, but it also has some sort of strange behaviors. So let's first of all think about the question of how is Carol going to react to this whole situation, right? So if you look at Carol in this table, Carol is a distant third place candidate, right? She only gets 75 points. She has no hope of winning. Okay, so Carol might anticipate this. She might see that she has no hope of winning, and she might decide to just drop out of the race, right? Why should she bother competing? But if Carol drops out of the race with exactly the same voter preferences, now Alice will win instead of Bob. So this does not make any sense, right? Bob was the winner. Alice is the third place candidate. She leaves, and now, sorry, Carol is the third place candidate. She leaves, and now Alice wins instead of Bob. Okay, this is very strange. So in terms of the jargon, what this means is that the border rule is being influenced by what we call irrelevant alternatives. So in this case, Carol is the irrelevant alternative. But in fact, the border rule is not the only voting rule with this property. It turns out there's a very deep theorem in social choice theory called Arrow's Impossibility Theorem that says that any reasonable preference-based voting rule is going to be sensitive to irrelevant alternatives in this way. Or another way that you can say the theorem is that if you have a voting rule which is insensitive to a relevant alternative, then it will turn out that it's not a reasonable voting rule. Okay, so the border rule has this problem, but in fact, many voting rules have this problem. In fact, plurality rule has this problem. Another problem with the border rule has to do with strategic voting. Okay, so let's think about Carol's supporters. Okay, so look at these people. There's 20% of the people, they think Carol's the best, and they prefer Carol to Alice, they prefer Alice to Bob. Okay, now, if they are aware of how the election is going to turn out, suppose they have access to the information on this table because they looked at some public opinion poll or something like that. Okay, they might say to themselves, you know, by voting for Carol, we're kind of screwing ourselves because basically, if we vote for Carol, Bob is going to win the election. We don't like Bob, right? Bob is our least favorite candidate. Why don't we lie? Why don't we pretend that instead we support Alice? If we pretend that we support Alice, then we can help Alice to win. And that's not, we wanted Carol to win, but at least Alice is better than Bob. So if they vote strategically in this way, watch what happens. If they switch their votes, right, they pretend that they like Alice more than Carol, that boosts Alice's score, and now Alice wins the election. So this shows us that the border rule can be manipulated through strategic voting. Okay, but again, basically almost every voting rule can be manipulated through strategic voting. There's a theorem called the Gibbard-Satterthwaite theorem that says that any reasonable voting rule is susceptible to strategic voting in this way. Okay, so these are sort of depressing results. Now, it might be that the problem here is that actually we've been thinking about voting the wrong way. Okay, so far all the rules I showed you aggregate preference data. In other words, basically what you ask voters is tell me who is your most favorite candidate, your second most favorite candidate, etc. And we're supposed to somehow aggregate that data to produce some kind of social decision. And in fact, Arrow's Impossibility Theorem applies specifically to these kinds of preference aggregation rules. So one way that people have reacted to this is to say that basically we're asking voters for the wrong kind of information. We're asking the wrong question. Maybe instead of preferences, we should make social decisions based on some other kind of data. So I'll show you three possible ways of doing that. Three voting rules: approval voting, majority judgment, and evaluative voting. Okay. So approval voting is based on the following idea. The idea is when you hold an election, the relevant question is not who is your most favorite candidate or what is your preference over candidates. The relevant question is which of these candidates do you find acceptable? Which of them could you live with? Right? Which would you tolerate? And so the point is that if you're going to ask people that kind of information, they can vote for as many candidates as they want. It's just that they can't provide more support for some candidates than others. So you're asking them to basically just tick a box next to each candidate if they find that candidate acceptable. Okay, and then basically you add up the votes for all the candidates, and the candidate who gets the most votes wins the election. So let's look at a simple example. So here's an example where there are 4 candidates, A, B, C, and D, and there are 8 voters who are these happy little people here. Okay, so in this example, for example, the first voter only votes for candidate A. Okay, The second voter votes for candidates A and B. The third voter votes for candidates B, C, and D, etc. Okay, so then we add up the number of votes in each of the columns. We get these numbers down at the bottom here. And so who gets the most votes? Candidate B. So B wins the election. B is acceptable to the largest number of voters. Okay. So this rule has been promoted by an American political scientist named Stephen Brams, and he's argued that it has many good properties. So it escapes from errors of possibility theorem basically simply because it's outside of the scope of errors of possibility theorem, right? Errors of possibility theorem is about aggregating preferences. Approval voting is not about preferences. It finds the compromise candidate, which is in some sense acceptable to the largest number of people. So it's a good rule for promoting something compromised. And it's somewhat resistant to strategic voting. It's not totally immune to strategic voting, but in a certain sense, it's resistant to it. So this rule has some attractive properties. Another rule we could look at is something which is called majority judgment. So the idea of majority judgment is that instead of asking voters for their preferences, you ask them to give grades to candidates on some kind of more or less objective scale. So the idea is the voters grade the candidates in the same way that a teacher assigns grades to students in a class, or the way that judges might assign grades to different contestants in a competition. And then the winner is the candidate who gets the highest median grade. Okay? So here's an example. So suppose there are 4 grades. So I'm just going to use sort of Olympic colors, right? So gold, silver, bronze medals, and then the last one is kind of like lead or Olympic gold or something like that, right? And again, we have these 4 candidates, A, B, C, and D, and 8 voters, and they basically grade the candidates as shown in the table. So for example, the first voter gives a gold rating to A and B, and she gives a lead rating to C and a silver rating to D. Okay. And so then basically the median grades are shown down at the bottom here. So for example, candidate A gets a median grade of silver. What that means is that a majority of voters are willing to give candidate A at least a silver grade, and a majority of voters are willing to give candidate A at most a silver grade. So silver is the unique grade where you can get majority support for at least that much and at most that much. That's what it means to say the median grade. So who has the highest median grade here? It's candidate B. Candidate B has a gold median grade, so candidate B wins the election. So majority judgment has been promoted by 2 French mathematicians, Michel Balinsky and Rita Laraki. They have written an entire book about how it has many very nice and attractive properties. So basically, the key thing about majority judgment is it makes a lot of sense when you can rate candidates on some objective scale of quality. It avoids errors of possibility theorem because, again, it doesn't deal with preference segregation, and it's somewhat resistant to strategic voting. A third possible rule is the evaluative voting rule. So the idea here is that you ask the voters to rate the candidates on a numerical scale. Let's say from 0 to 10, and the winner is the candidate who has the highest total score. Okay. So, for example, suppose that the voters evaluate our 4 candidates according to the numbers in this table here. We add up all the numbers in each column. We get these values down at the bottom. Who has the highest total? It's candidate B, who has a total score of 37, so candidate B wins the election. So what is this good for? Well, the advantage of this rule is it helps us to aggregate the intensity of preferences. Okay, so the problem with things like the border rule or plurality rule is that they allow a voter to say, I think Alice is better than Bob. But they don't allow a voter to say how much she thinks Alice is better than Bob. So the advantage of these numerical ratings is that they allow voters to express their preference, the intensity of their preferences. Again, this escapes from errors of possibility theorem. The big disadvantage of this rule is that it's very susceptible to strategic voting. There's an obvious strategy where voters can exaggerate their rankings for different candidates. Okay, and in fact, basically, in the limit, what they will do is they will assign the maximum score of 10 to all the candidates they like, and the minimum score of 0 to all the candidates they don't like. And if they do that, they basically end up behaving like approval voting, which is not terrible, right? Approval voting is pretty good, but it's not really what we wanted when we set up the evaluative voting procedure. Okay, so at this point, I've showed you a bunch of different voting rules, and you're probably asking the question, which is the best voting rule? Right? You shouldn't answer, right? Well, there is no best voting rule. Okay? Anybody who tells you that there's a best voting rule is telling you something. There's no such thing as the best voting rule, because the best voting rule depends upon the nature of the social problem you're trying to solve. It depends upon the kind of information available to you, and what is the objective of your social decision. So, for example, there are some social decisions where there is an objectively correct answer, right? Where basically any answer you propose is either objectively correct or incorrect. There's a fact of the matter. And in these cases, you want a voting rule that's going to aggregate the information and the opinions and the perspectives of the different voters to try to make the best possible guess about that correct answer. So examples would be things like a criminal trial jury, right? The defendant in a criminal trial is either guilty or innocent. This is an objective fact. And the goal of the jury is to ascertain this fact. Another example would be the International Panel on Climate Change. There are these working groups which try to develop some kind of consensus statement about certain scientific questions about, the probability of the Antarctic ice shelf melting or something like that. So again, they're trying to come up with the best possible, most accurate possible statement about some matter of scientific fact, right? But there are other social decisions where objective truth is not really the issue. There is no objective truth. You basically just have different people who have different preferences, different desires, and you have to find some reasonable compromise between the conflicting desires of different people. Now, in these cases, we can distinguish between two subcases, right? In some situations, there is a substantive ethical question that we're trying to solve, right? There are issues of fairness or social justice. For example, something like how to distribute resources. So in these cases, social choice theory basically is grappling with what is essentially an ethical problem. In other cases, there isn't really a substantive ethical issue. It's just different people want different things, and you have to find some reasonable rule which is not going to produce a totally insane outcome. So, for example, if a bunch of people are trying to decide where to go for dinner, different people want to go to different restaurants. This is not a deep ethical problem, but nevertheless, you still want to make the decision in a reasonable way. Then there are decisions where we can assess the merit or quality of the different candidates on some kind of objective scale, right? Like this is what we were talking about with majority judgment. So, for example, if you think about a hiring committee, right? The hiring committee interviews different candidates, then they want to decide who they're going to hire. Presumably, this is supposed to be based upon some kind of more or less objective evaluation of which candidate is the most qualified or the best candidate for the job, right? Or you have juries, which are supposed to assign a prize to some other competition. Or another example is the election at jurisdictions where judges or prosecutors are elected. This is a technocratic position. You should be electing people based upon some measure of their expertise or their competency. But there are other kinds of elections where merit is not really the issue, right? There are some elections where what you really want to do is choose people who are going to accurately represent the views and values of the voters. So this is the case when, for example, you're electing a parliament. So basically, the point is that different social decisions involve different criteria and different objectives, okay? And that means different rules are going to be appropriate in different situations. And so one way that we can make the statement precise is that we can encode the various desirable properties of our voting rule as precise mathematical formula, precise mathematical statements, which we call axioms. And different axioms are going to be desirable in different situations. And then many of the major theorems in social choice theory basically take the form of saying that such and such voting rule is the unique voting rule that satisfies a particular combination of axioms. Okay, so that means if that particular combination of axioms is appealing to you, if you find it compelling, that means that you have to use that particular voting rule. Okay. However, social choice theory is not just about preferences and rankings and quality assessments. It basically is a broader topic which involves aggregating opinions of any kind. Okay, so now I'm going to talk about a different kind of social choice theory, which is called judgment aggregation. So judgment aggregation starts with the following scenario. Suppose that we want to democratically decide several binary questions. So when I say binary, what I mean is questions which have a yes or no answer. Okay. So let's call a set of answers to these questions with you. So one obvious idea is that you could decide each of these questions separately using a majority vote, right? That's the obvious way to decide binary questions. The problem is that if these questions are logically interconnected, then this procedure can lead to a logically consistent collective view. Okay, so let me show you a simple example. Suppose we want to decide three questions, right? So the first question is, should we raise or lower taxes? Should we increase government spending? And should we reduce the deficit? Okay. So 33% of the voters want to increase government spending and they want to reduce the deficit. And so therefore, obviously, they accept that it's not possible to lower taxes. And another 33% of voters, they want to lower taxes, and they also want to reduce the deficit. And so therefore, obviously, they accept that it's not possible to increase government spending. And the rest of the voters want to both lower taxes and increase spending, and they don't care about the deficit. So what we see now is that a majority of voters want to lower taxes, a majority of voters want to increase government spending, and a majority of voters want to reduce the deficit. This is obviously a logically inconsistent collective position. Notice that this occurs even though every single individual voter has a logically consistent view. Okay? So this might strike you as a kind of an artificial toy problem, but it's important to note that very similar problems arise in many collective decisions, including jurisprudence, facility location, classification, preference aggregation. So this general problem of aggregating binary views is called judgment aggregation. Now, looking at this example, you might think that the problem here is that we use majority vote to decide these questions. Maybe if we used some other voting rule, we could escape from this silly outcome, right? So now we come to a whole series of impossibility theorems, which have been proved by different people in different guises over many years, but they all have the same kind of general format. So they all say something like the following: consider any judgment aggregation problem which has a non-trivial logical structure. In that case, any judgment aggregation rule which operates on a question-by-question basis and has other good properties, like not being a dictatorship, will yield logically inconsistent views, at least in some situations. So we have a bit of a problem here. So basically, our goal now is to find some kind of judgment aggregation rule which has good properties, but which is guaranteed to always yield a logically consistent collective view. And in virtue of these impossibility theorems, such a rule cannot operate on a question-by-question basis. It has to take some kind of more holistic approach. So how could we take a more holistic approach? Well, one thing we could try to do is to be as majoritarian as possible in some sense, while still respecting the constraint of logic and consistency. Okay, so this is some work that I've done with Klaus Nering and Pivato, which I'm going to talk a little bit about now. I'm going to talk about something called V and rule. So let Q be the set of questions on the agenda that we're trying to solve. So in the example I showed you earlier, Q had 3 questions: lower taxes, raise spending, and decrease the deficit, right? And let V be a view. So what is a view? It's just something which gives a yes or no answer to each of these questions. Okay. So now for every single question in the agenda, let MQ of V be the fraction of voters who agree with the view V on the question Q. And then let's define the score of this view V. This be the sum of these MQs over all questions. So basically, it's the sum of the fraction of voters who agree with the view V on each of the questions. Okay. And so the median rule just picks the logically consistent view, which has the highest possible score according to this scoring system. You can think of this as a very natural way to think about the idea of majoritarianism in the context of judgment aggregation. And so in a recent paper with Klaus Nering, we characterize the median rule with 3 axioms, which I'm going to show you now. So the first axiom is roughly stated, it's supermajority efficiency. So what this says is that the rule should try to agree with majorities on as many issues as possible. Okay, and when it has to make trade-offs between majorities in different questions, it should always prioritize larger majorities over smaller. Second axiom is continuity. This just says that the rule should be stable against small perturbations or measurement errors. And the third axiom is reinforcement. So the idea of the reinforcement axiom is you can imagine taking your population of voters and splitting it into 2 smaller populations, let's say 2 states, okay? And then you apply the judgment aggregation rule separately to each of these smaller subpopulations. Suppose that for each of the smaller subpopulations, the judgment aggregation rule chooses the view V, same view. In that case, the axiom says when you put all the voters together into one big population, the rule should also choose V. Okay, it wouldn't make sense if it chose V through the both subpopulations, but then you put them together and you get a different output. So the theorem says that if you start with any judgment aggregation context, which is non-degenerate in a certain way, basically this means there's no logically redundant issues, then the median rule is the only judgment aggregation rule that satisfies the three axioms: supermajority efficiency, continuity, and reinforcement. Okay, so that's about all I have to say about social choice theory. So what I'm going to do now is I'm going to move on to the second topic, which is decision theory. So decision theory basically is about the question: how should a rational agent make decisions in the face of uncertainty? But there's a kind of a more fundamental question lurking here, which is what exactly do we mean by rationality anyways? So most of the models of decision theory conform to something that you could call the Humean paradigm, after David Hume, which is to say that rational decision making is going to combine two different ingredients. Okay, the first ingredient is the agent's beliefs about the world, the agent's beliefs about the background conditions of the decision. And the second ingredient is the agent's desires about the final outcome that she wants to achieve. Okay. Notice that when we talk about rational decisions, we don't mean correct decisions. A rational decision could be wrong if it's based on incorrect beliefs. And we don't necessarily mean ethical decisions, right? A rational decision could be unethical if the agent's desires are unethical. So rationality is distinct from questions, the epistemic question of factual correctness, and it's distinct from ethical questions. So let's look at this Humean paradigm. So rational decisions should combine beliefs about background conditions with desires about the final outcomes. So let's try to be a bit more mathematical now. In normative economics, the way that we normally try to mathematically represent an agent's desires is using a preference order or a utility function. And the way we typically represent beliefs is using a probability measure or something like a probability measure, some kind of probability-like information. And then typically, in these models, the rational decision is going to be the decision which maximizes the expected value of the utility function. Okay, but the important point is that we don't just sort of assume that this is the case, right? Like this is not an axiom that you want to maximize expected utility. Okay, what we want to do is derive that kind of a decision rule from more basic or fundamental principles, from basic normative axioms. Okay. So what kind of axioms do we have in mind? Well, the weakest axioms are just going to be axioms that require the agent's decision-making to be internally consistent or not self-defeating or self-contradictory, right? So for example, one thing we want to rule out are preference cycles like this one, right? So this preference cycle says the agent prefers A to B, she prefers B to C, and she prefers C to A. So we think of this kind of a preference cycle as kind of quintessentially self-defeating behavior. This is the kind of thing that we would want to rule out with an axiom. Some of the stronger axioms have more the flavor of logic or some kind of Bayesian reasoning. They're basically talking about how the agent should respond to the arrival of new information. Right? If she learns new information, she should update her decisions in some kind of reasonable way. And then we have axioms which broadly go under the heading of dynamic consistency, which talk about how the agent should respond to a change in the decision problem. So for example, suppose the menu of feasible options expands, or suppose the menu of feasible options shrinks. Suppose the decision problem changes in some other way, the agent should respond to that in a rational way. Okay, and then the idea is we put these axioms together and we derive some decision rule, like, for example, expected utility maximum. All right, so I've mentioned preference order several times so far. When we were talking about social choice theory, I said voters have preference orders. So now let's be a little bit more specific about what we mean by preference order. So let A be the set of all alternatives which are logically possible, or all alternatives which are even conceivable to the agent. Okay. So a preference order on A is a binary relation, which I'm going to represent using this greater than or equal symbol. Okay, we read this symbol as weakly preferred, right? So the preference order is a binary relation which satisfies three axioms. First is reflexivity, which says that every alternative in A is weakly preferred to itself. Okay. The second is that the relation is complete. So for any two alternatives A and B, either A is preferred to B or B is preferred to A. And the third requirement is transitivity, which is that for any three alternatives A, B, and C, if A is preferred to B and B is preferred to C, then A should be preferred to C. So this is the axiom of the rule about things like preference cycles. Okay, so what does the agent do with this preference order? What is this preference order? How does it affect the decision-making behavior? Well, suppose that on some particular day, B is the set of all alternatives which are feasible to the agent. So this is a menu, so A is the set of all alternatives which are even logically conceivable, logically possible. B is going to be the set of alternatives which are actually feasible. It's the menu, okay? So if the rational agent has a particular preference order, then what she should do is choose some element from this menu, which is maximal relative to her preferences. And so what do I mean by maximal? What I mean is that C is preferred, weakly preferred to every other element in the feasible set. Okay. Notice I was very careful here to not use the definite article. I used the indefinite article and element because I'm not assuming that the maximal element is unique. There might be many maximal elements, and if there are many maximal elements, it doesn't matter which one you pick. But you should pick at least some maximal element. That is what rationality consists of according to this model. Okay, so that's a claim. So you might say, well, why is that rational? Why should I be convinced that rationality means choosing the element which is maximal for some preferences? Well, now I will show you an example of an axiomatic characterization to try to convince you of that. Yeah, I'm going to try to sort of provide an argument for why a rational agent should always choose an element from the feasible set which is maximal. So consider the following axiom. So here in this picture, A, the universe of all conceivable alternatives, is the big white box. And inside of it, we have this gray ellipse B, or B1, which is the set of all feasible alternatives, the menu of feasible alternatives. And suppose that when the agent is presented with the menu B1, she chooses anything from the set B1. Okay, so P1 is the set of all things that she would be willing to choose. Okay, that she would find in some sense optimal. Okay, if the set B1 was the feasible set. And now suppose that the feasible set shrinks. Suppose that the feasible set gets smaller, it's reduced to set B2. Okay, so some of the feasible items are removed from the menu. But suppose that the set B2 still intersects that C that she chose from. Okay, and the intersection between B2 and C1 is this set C2. The intersection of the feasible set B2 and the original choice set C1 is not empty, and it's C2. So then the axiom says, in this case, when presented with the feasible set B2, the agent should always choose elements from the set C2, and she should only choose those elements. Okay, so if you think about it, this makes sense, right? Basically, if the agent was willing to choose something from the set C1 before, okay, and we make the feasible set smaller, but things from the set C1 are still available, then she should choose those things from that set, right? It would be crazy for her to choose something outside of that set. So here's the theorem by arrow. So an agent's choice behavior satisfies this axiom if and only if there's some preference order on the universe of alternatives, such that the agent always chooses elements or alternatives that are maximal according to that preference order. Okay, so this is kind of an axiomatic characterization of preference maximization. Yeah. So if you think this axiom is compelling, if you think this is a reasonable axiom to apply to decision making, this tells you that rationality involves maxims in respect to preferences. If you don't think this axiom is compelling, then this theorem doesn't matter. So far I've been talking about decision making with certainty. Let's now look at a situation where there's uncertainty. Okay, because most real decisions involve some degree of uncertainty. Now suppose that A is some finite set of possible outcomes. Well, I'm going to define a lottery to be a function delta, which assigns a probability between 0 and 1 to each of the items in the set A. Okay, and the sum of all the probabilities has to add up to 1. So the interpretation here is that delta represents some random device or random procedure, and for any alternative A, delta of A is the probability of obtaining the outcome. That's what we call the lottery. So let capital delta sub A be the set of all such lotteries. We can visualize that as a kind of a triangle, like this, or a higher dimensional triangle. It's called a simplex. Okay, so the vertices of this triangle represent lotteries which are guaranteed to yield a certain alternative with probability 100%. Okay, so for example, this corner here, that is the lottery that yields the outcome A with probability 100%. This corner here, that is the lottery that yields the probability B with probability 100%. And this lottery is guaranteed to give you C. This point here, halfway between A and C, that represents a lottery where you flip a fair coin. If the coin lands heads, you get A. If the coin lands tails, you get C. Okay? And all of the other possible lotteries can be represented geometrically as points instead of this triangle. So in many decisions, we have to choose between actions which have uncertain outcomes, right? There's some degree of risk in the world. And we can represent these as choosing between different lotteries. In other words, choosing between different elements of this probability simplex. Okay, and for a rational agent, the choice between different elements of the probability simplex should be governed by some preference order on the simplex. That's the theorem I showed you a few minutes ago. So now the question is, what sort of preference order should we have on this simplex? Right, what would be a rational preference order to put on the simplex? So one might argue that the preference order on the simplex should satisfy certain consistency conditions. So here's an example of a consistency condition. So suppose that I have three lotteries, alpha, beta, and gamma. Three arbitrary points in the simplex. Now I'm going to construct two new lotteries. Okay, the first is the lottery alpha prime, which is halfway between alpha and gamma. So the way alpha prime works is you flip a fair coin. If it lands heads, you get the same outcome as alpha. If it lands tails, you get the same outcome as gamma. So it's a kind of a 50-50 mixture between alpha and gamma. And we have another lottery beta prime. It's the same idea. You flip a fair coin. If it lands heads, you get the same outcome as beta. If it lands tails, you get the same outcome as gamma. So it's like a 50-50 mixture between those two. Okay. All right. So now the axiom that I have in mind says the following. It says, if you think that alpha is better than beta, then you should think that alpha prime is better than beta prime. This is perfectly reasonable because if you think about it, what happens when you choose, if you flip the coin and the coin lands heads, okay, then alpha is giving you exactly the same payoff as, alpha prime is giving you exactly the same payoff as alpha, and beta prime is giving you exactly the same payoff as beta. So the choice between alpha prime and beta prime is equivalent to the choice between alpha and beta. So if you think alpha is better than beta, then you should think alpha prime is better than beta prime. On the other hand, if the coin lands tails, then alpha prime and beta prime both give you the same thing. They both give you gamma. There's no difference between them. So in that case, it doesn't matter which one you pick. Okay? So the only case that matters is if the coin lands heads. And if the coin lands heads, then the choice between them is the same as the choice between alpha and beta. This is the axiom. If you think alpha is better than beta, you should think alpha prime is better than beta prime. So this axiom is called independent. And it has a nice geometric consequence, which is that when you look at the different sets of this preference order, they're all going to be kind of parallel planar slices through the template, something like that. Okay, so now we come to a very important theorem in decision theory, which is the von Neumann-Morgenstern theorem. So it says the following: suppose that I have some preference order on my probability simplex, and suppose that it satisfies the independent axiom I just told you, and it's also continuous. Okay, which just basically means that if the agent strictly prefers alpha over beta, and gamma is some other lottery which is very close to beta, then the agent should also strictly prefer alpha over gamma. So it's just saying preferences are kind of stable against small perturbations or jiggles. Okay, so these are the two axioms. So the theorem says that the preference order satisfies these two axioms if and only if there exists some function u mapping the alternatives into real numbers, such that the agent always prefers lotteries yielding the highest possible expected value for that utility function. Okay, so what this means is for any pair of lotteries, gamma and delta, the agent prefers gamma over delta if and only if the expected utility of gamma is greater than or equal to the expected utility of delta. So to see what this expression means here, what am I doing here? This is the sum over all alternatives of the probability gamma gives to that alternative times the utility of that alternative. So this is the expected utility of gamma, the expected value of the function u for gamma. And likewise, this is the same thing for delta. So this theorem tells us rational agents should maximize expected utility. And furthermore, what's interesting is that this function u, the so-called utility function, in this representation is almost unique. Okay, it's unique in the following sense: if u prime is another function which also satisfies this representation, then there exists a positive constant a and another constant b, such that u prime is a times u plus b. So the idea is that u prime and u are related kind of the same way that Fahrenheit and Celsius temperature scales are related, right? They both measure the same physical quantity, which is temperature. This function u is typically called the cardinal utility function, and so one advantage of the von Neumann-Morgenstern theorem is not only does it give us a very specific theory for rational decision making, but it also tells us now that there is a natural way to measure the intensity of an agent's preferences. Right? The function u can be thought of as measuring the intensity of the agent's preferences over the different alternatives. Okay. So one problem with the von Neumann-Morgenstern function is it is assuming that the agent knows how to assign objective probabilities to different outcomes, right? She knows the probabilities. But there are many decision problems we face where there's uncertainty and we really don't know what these probabilities are. Okay? And so around the same time as von Neumann and Morgenstern, Savage looked at this problem, and he proposed the following model of decision making. Savage said, well, suppose there's some set as a possible state of nature. So what's a state of nature? A state of nature is just a complete description of everything about the world that might be relevant to your decision making. Okay. Now the point is, we don't know what is the true state of nature. Okay? In fact, a priori, we don't even know what is a good probability distribution of a set of possible states of nature. So the set of states of nature just encodes all information about the world that is unknown to us. It is a model of uncertainty about the world. We also suppose that there's some other set X of outcomes. These are the things that are going to come out of the decision. They're the results of the decision. Okay, so this could be, depending upon the situation, these might represent consumption level of material goods or chaos of some kind. And then in the Savage model, an act is a function alpha that maps every state of nature into one of these outcomes. The idea is you're presented with a menu of possible acts. You pick one of the acts from the menu. Then the state of nature is revealed. And depending upon what state of nature occurs, the act is going to deliver different possible outcomes to you. Okay, so this is how we model decision making under uncertainty. So now let capital A be the set of all possible acts, all possible functions mapping states into outcomes. So a choice between actions with uncertain consequences can be modeled as a choice between different elements of the set A. So basically, now a rational agent should make choices over the set A in terms of some preference order on the set A. This is the theorem that I showed you about 10 minutes ago. Rational choices should be governed by preferences. So the question now is, what sort of preference order should we have on this set A of Savage acts? So up at the top of the screen here, I'm just basically reviewing the notation I put in the previous slide. Now we come to Savage's theorem. So Savage's theorem says, suppose I have a preference order on the set A which satisfies 6 axioms, which I'm not going to tell you because I don't know, but they're axioms which broadly speaking encode some kind of normative, reasonable normative criteria. Then there exist 2 things. First of all, a real value function on the space of outcomes, which again plays the role of a kind of a cardinal value function. And second of all, a probability distribution on the space of states of nature, such that this preference order always prefers the acts that yield the highest expected utility. So what that means is, given any 2 acts alpha and beta, the agent prefers alpha over beta if and only if the expected utility of alpha is greater than the expected utility of beta. And the way that you read this expression is the sum over all possible states of nature of the probability of that state occurring times the utility of the outcome that alpha would yield in that state. So in that sense, this is the expected utility of the act alpha, and likewise, this thing over here is the expected utility of the act beta. Okay. So the Savage model is very nice because it kind of provides us with a very mathematically precise realization of the Humean paradigm, right? The utility function U describes the agent's desires for different outcomes in X, while the probability distribution P describes her beliefs about the unknown state of nature. Okay. So one criticism of the Savage model, though, is that it requires the agent to actually form a probabilistic belief about the state of nature. And there are some situations where your uncertainty about the world is so radical that you just have no idea how you would even perform it, how you would even construct this probability, right? You just don't have enough information to pin down a unique probability for different events to occur. And so this is something which in decision theory referred to as ambiguity, and a lot of work in modern decision theory is about proposing methods to cope with this kind of ambiguity. So there are many different approaches. I'm just going to show you one. It's called Maximin expected utility. So this is an approach which has been characterized by Saki Balboa and David Schneidler. So Saki Balboa is at Paris. So in their model, P is now not a single probability distribution. P is a set of probability distributions on the space of states of nature. This is like the set of all possible probability distributions that the agent considers to be remotely reasonable or possible in some sense. So the true probability distribution is one of the elements of the set. So for any probability distribution little t and big T, let's use this symbol E sub P to mean expected value with respect to U. Now let U once again be a utility function and a set of outcomes. So in the Maximin expected utility model, for any acts alpha and beta, we say the agent should prefer alpha over beta if the minimum over all possible probabilities of the expected utility of alpha is greater than the minimum over all possible utilities of the expected utility of beta. Okay, so the idea is basically this describes an agent who is extremely risk averse or pessimistic. So given any act, the way she evaluates that act is she asks, so what is the worst possible expected utility that I can get from this act, right? What's the worst possible expected utility over all plausible probability distribution? That is how she evaluates different acts. And then she chooses the act which maximizes this worst case possible expected utility. Okay. So there are many other interesting things to say about decision theory, but in the interest of time, I'm now going to move on to the third topic, which is social welfare. So social welfare starts with the observation that a moral system should generate rational behavior, right? I mean, it would not really be very useful to have an ethical system which causes you to engage in self-defeating irrational behavior. The moral agent should conform to the principles of decision theory that we just talked about. Likewise, government policy ideally should also be rational, and so government policy should also conform to the principles of decision theory. So this suggests that moral agents and governments should use a preference order or utility function to evaluate different possible courses of action. And so the question is, what preference order or utility function should they use? This is basically what social welfare theory is about. And one natural way to construct a preference order or utility function is using something called utilitarianism, which to be probably heard of it. So roughly speaking, utilitarianism says that we should always choose the action that maximizes the sum total well-being of all people in society. So here's one way that we can formalize that. So let's suppose that the numbers from 1 to capital N are used to represent sort of all the people. Okay? Let X be some set of social outcomes. So an element of X is just kind of like a complete description of everything about how society is organized, how resources are allocated, tax policies, whatever you think is important. For every individual I in my set, let UI be a real value function on a space of social outcomes. So like with your I utility function. The idea is given any social outcome in X, UIX is a quantitative measure of the well-being the person I would receive in the social outcome X. And then for any social outcome X, we define capital W of X to be the sum of the utilities of all the people in society. From total well-being induced by this outcome. So for example, there were 4 people in society, Alice, Bob, Carol, and Dave. W of X would be Alice's utility plus Bob's utility plus Carol's utility plus Dave's utility. So if we do this, we get a function, capital W, which maps every social outcome to some real number, and that is what we call the utilitarian social welfare function. The utilitarianism says we should choose the quality that maximizes W. So this is something which has been around in moral philosophy for like 200 years. Okay, and I mean it's somewhat controversial. There are arguments about it. It turns out that there's a surprising link between utilitarianism and the theory of rationality I was telling you a few minutes ago. So let's consider a hypothetical moral agent, like this could be, for example, the government. Okay. So Harsanyi in 1955 proved the following theorem. It said, suppose that all people in society are expected utility maximizers described by the von Neumann-Morgenstern model, which I showed you a few minutes ago. And suppose that the moral agent, like the government, is also a von Neumann-Morgenstern expected utility maximizer. And furthermore, she obeys the ex ante Pareto principle. So the ex ante Pareto principle says, if every single person in your society prefers the lottery alpha to the lottery beta, then the moral agent should also prefer alpha over beta. Okay, so you can think of this as a kind of a very minimal democratic principle, right? The moral agent should respect a unanimous consensus of all the individuals in society. So the theorem says, with these simple hypotheses, the moral agent must be a weighted utilitarian. In other words, the von Neumann-Morgenstern utility function of the moral agent must be some weighted average of the von Neumann-Morgenstern utility functions of all the individuals in society. So this is extremely surprising, right? We start with very, very simple, minimal, uncontroversial premises, namely the von Neumann-Morgenstern theory of rationality, which I already showed you is characterized by a pretty compelling theorem. And this Pareto property, which is just a kind of the most minimal democratic condition you can imagine. And what comes out is utilitarianism, which is a very specific substantive moral philosophy, which, as I said earlier, is actually quite controversial. This is actually quite a surprising theory. Now, one could say, well, this theorem is based on the von Neumann-Morgenstern model, and the von Neumann-Morgenstern model is somewhat limited. We talked about Savage. So can we prove a similar theorem in the Savage setting? And it turns out that we can. A similar theorem can be proved in the Savage model of uncertainty. And this is some work that I did with Philippe Marjan. And so basically, in our model, we require collective purposes to satisfy four desiderata. The first is statewide dominance. So the idea is you compare two policies, two courses of action. If policy X is guaranteed to always yield better outcome than policy Y in every possible state of nature, then society should prefer X over Y. Okay. The second axiom is the ex ante Pareto axiom, just like in the Harsanyi theorem. So if every single individual prefers policy X over policy Y, then society should prefer X over Y. The third is the ex post Pareto axiom. Now we're comparing outcomes. It says if every single individual prefers the outcome X to the outcome Y, then society should prefer outcome X to outcome Y. So the difference between these two Pareto axioms is that the ex ante Pareto axiom is about comparing policies before uncertainty is resolved, whereas the ex post Pareto axiom is about comparing outcomes after uncertainty is resolved. Other than that, they're very similar in flavor. And the last axiom is continuity, which says that references should be stable against null perturbations or errors. And so basically what we show is the following. I should say that the statewide dominance axiom, you can think of it as kind of a minimal rationality condition. In fact, it's arguably the most minimal rationality condition possibly imposed. And likewise, with two Pareto axioms, you could think of them as minimal condition. What we show is the following. Collective preferences satisfy these four desiderata if and only if four things are true. So first of all, every single individual is an expected utility maximizer. So notice that unlike Harsanyi, we do not assume people are expected utility maximizer. This is actually a constant. Every single individual is an expected utility maximizer in the Savage sense. Social preferences, the preferences of the social agent, of the moral agent, also maximize the expected value. They maximize the expected value of the social welfare function. Third of all, this social welfare function is utilitarian. In other words, it is a weighted average of the utility functions of the individual. So this is and finally, every single person in society has the same probabilistic beliefs about the uncertainty of the world. Okay. So basically, what comes out of this is two things, right? First of all, we get, like Savage, we get an axiomatic characterization of expected utility maximization. That's one of our consequences. And second of all, like Harsanyi, we conclude that the social welfare function should be utilitarian. Okay. There's that theorem again. So the problem in this theorem, the troublemaker is part B, because part B says everyone has the same beliefs. Okay, so it rules on heterogeneous beliefs. And this is very unrealistic because there are many decision problems where reasonable people can disagree in a probabilistic beliefs. So you could actually look at part B as kind of an impossibility theorem, which actually extends an earlier famous result by Philippe Marjan from 1990. So the problem is, how can you escape from this impossibility theorem? What can you do? Well, one diagnosis is the problem here involves the ex ante Pareto axiom. The ex ante Pareto axiom is about aggregating people's ex ante preferences over policies, and people's ex ante preferences over policies combine two fundamentally different kinds of information. There's welfare information, which is what the utility that they would get from different outcomes, and then there's doxastic information, which is about their beliefs about the unknown state of nature. Okay, and the thing about the ex ante Pareto axiom is it forces us to aggregate both kinds of information at the same time, and that doesn't make sense because they're two fundamentally different kinds of information. Arguably, you should treat these two kinds of information separately. You should aggregate them using different rules according to different criteria. So I've explored this idea in several recent papers, and basically the common idea in these papers is that they weaken the ex ante Pareto axiom, and they axiomatically characterize a utilitarian social welfare function while still allowing heterogeneity of individual beliefs. Okay, so I'm basically done. So let me just kind of summarize. So what I discussed in this lecture was some of the main themes of normative economics. So this subject lies at the boundary between mathematics, economics, philosophy, political theory, and increasingly theoretical computer science. It uses methods of theoretical economics to address fundamental questions about the nature of rationality, democracy, social justice, and it has applications to the design of democratic decision processes, the criteria that should guide public policy decisions, and the evaluation of the consequences. And so a better understanding of these issues is essential to improving the performance of government and the quality of public policies. So thank you very much for your.